I'm Bob McPherson, and this is a brief summary of my final project for big data analytics called Forensic Server Log Analysis with Hive and MapReduce. Server security and data breaches are increasingly in the news, and forensic analysis of server logs is necessary for identifying vulnerabilities, performing damage assessments, prescribing mitigative measures, and collecting evidence. Massive collections of server log data are collected, and these are difficult to analyze with conventional tools. The Hadoop, MapReduce, and Hive software stack provides a solution. You can use HQL queries that are very much like SQL, for those that are familiar with that, to assist in performing forensic analysis. You can also use HiveQL to produce analytical data sets for other software tools such as R and Mount. Methods of analysis will include performing fuzzy searches for keywords and terms, time aggregations of web log variables for trending, performing sorting to identify potential problem sources, creating analytical data sets that are suitable for further analysis. The data needed to run the analysis is provided in the package for this final project, but for others that may be interested, I've got them stored out on my Google Drive location at this URL here. And you can also search on my name, robert.l.mcpherson. You might find it that way. The data consists of Apache combined format server log files. Server logs 1 through 6 are from Amazon's sample collection, but I add an additional file, number 7, which contains examples of log entries with known security breaches. The software needed to run this analysis should already be loaded on everyone's machines that have been through this class. For others, you need a Hive working Hive environment. You need Hadoop, you need MapReduce. It also could be helpful to have Mount and R for some additional statistical analysis. However, the focus of the project's on Hive. Hive is excellent for ad hoc customized searches, which is beneficial for forensic analysis. First, we're going to load the data and start Hive. And this should look familiar to most of you that have been through the class, but I'm just adding it here for review, just to get us started. So we'll start Hive at the command line. Now we're going to add a jar file that allows us to parse regular expressions. This jar file is called a Serday serializer deserializer. Some of you remember this as well from an earlier assignment, but we'll just repeat it here for review. And now I'm going to set header equal to true so that the results that come back from my queries will include the header. It's optional, but I like being able to see the headers to refer to. Now we'll simply create the table. I'll copy and paste that here. That should look familiar as well. Here you have your regular expressions that parse the log files, and that table stored correctly. Now we're simply going to load the data. All 7 of the Apache log files, including that 7th one I included that has some known attacks. And we see that all 7 loaded successfully. And now that we have our data loaded, we can actually start a discovery process for specific attack vectors. We're going to find patterns within the request field. This field shows URL information for the resource or web page that was requested. Many attacks leave telltale fingerprints behind within this field that can be identified through the like operator using HQL. Next, we're going to do an example of a direct search on a file inclusion attack. Here's some HQL. Looks very much like SQL. Has the like operator that should be familiar to many of you. However, I've added a function here that says lower. And this is something unique to HiveQL compared to most databases anyway, in that the like operator is case sensitive for HiveQL. So I'm changing everything to lowercase with this lower function. And then you'll see after the like operator a number of key terms that relate to folders that exist at the root of most systems that would have Apache loaded on them. Also, I'm looking for .exe executables as well as .ini. And this one here is probably the real workhorse of the whole thing. The very last line, it's got 2 dots. It's sort of the Swiss Army knife of file traversal that should be very familiar to most of you. And these are pretty ubiquitous in these kinds of attacks. You can almost write a query with just that and probably catch a lot. So let's go ahead and run this and see what we get. All right, so while that's running, let's take a look here at another attack. It's called command injection. This attack tries to disguise commands with HTML URL encoding. The following query includes keywords for some common examples. Here you've got ampersand comma, you've got 20 echo for %20 echo. In this case, the percent is part of the like operator looking for any characters that precede that. And then you've got 60 ID. So these are very commonly used in these kinds of attacks. They can be hard to spot when you're just eyeballing a log file, and this query will ferret them out pretty efficiently for us. Now let's go back and see if our query ran. It did, and we have several results, and these are actual examples of attacks. And you can see the ubiquitous dot command here, or the dot traversal, file traversal. And we've also got a system.ini down here in the bottom left. And so we have an executable file as well. So we're able to pretty readily identify those. I won't run this command injection. We don't have enough time to run all of the possible queries. I have a number more that I didn't include in this presentation, but I can show you the results here, and there were quite a few actual attacks that were identified by this method. Let's move on to tracking and tallying failed request statuses. Often an attacker might experience a number of failures before hitting on the right combination, which brings success. This isn't necessarily an indication that an attack has taken place, but it could be a good starting point for further investigation. Now we're going to look for hosts with the most failed requests. Statuses of 100, 200, or 300 series ranges indicate successful client requests and server responses. However, those statuses in the 400 range or 500 range are failed requests. 400 tends to be client side, and 500 would be problems on the server side. We're going to do some time aggregations, and we'll couple that with the status codes, and we'll get some interesting things. We'll be able to identify hosts over time that may have had a number of failed requests. And we'll have to zero in on this time field right here. That's how it appears in the server logs. And you've got day, month, and year, and that's what we're going to focus on out of the string. The string also does include hour, minute, seconds, and then the 4 digits to the right are time zone. This query here, which looks kind of jumbled up, I had to kind of cram it into the slide here, looks much neater in my actual code set. But what it does is it simply takes my alphabetic month and converts it into a numeric day so that I can sort on it more readily. The result is shown down here in the bottom where I've got month, year, month, day, and year. And now I'm going to copy that query from my actual code set here, paste it into the command line, and then we'll run that. Okay, so that view loaded correctly. Now a view isn't going to run right away. You're just simply loading a framework in essence. But now that I've got that view created, I can now create some additional views on that. And that's a handy thing about Hive as well, is that you can chain some of these views together and do some rather complex things with the data. So here we're going to add a view. And this view, if you can see that, enables the creation of a time series by day over multiple years and months. So the preceding query was aggregating, creating some new fields by month and by year. Now I want to do it by day, by month, by year, so that I can actually look at a time series by day over multiple months and multiple years. So I'm just using the preceding view, adding this, and that view ran fine. And now I'm going to add 2 more views. And the first view looks for unsuccessful server calls as a time series by year, month, and day. The second view looks for successful server calls. And so I can create a ratio out of the two. So let's go ahead and run those. Paste the first one in here. Okay, that got created successfully. And we'll put the second one in here. Of course, you could run these all in one chain all together. I'm just trying to explain as I go, so I'm running them individually. So we got the second one in here that looks for successful ones. And now, with those, I can do a join statement, which is what this query does, and I can create a ratio of the unsuccessful requests to successful requests over time. And here's a sample of what you get in the end. You have the year in the first 4 digits, then the month, then the day. It's very sortable. And then you've got the fail ratio on the right is what that produces. But we'll go ahead and run that. Okay, so that's running. And I can export the data for further analysis, which I've already done here. But this essentially is just showing that you just take the same query I just ran, and at the top of it you put insert overwrite local directory, and then the next line, second line, shows where I'm going to place that, and that's placing that in a shared folder location between my virtual machine and my local computer. So with that exported data, I can actually take it as is with the delimiter that's standard in Hive. It's an odd looking delimiter. It looks like it's a caret with a capital A. But it's handy because it's unlikely to be confused with any other delimiter like commas and numbers. And so here I've got some R code. First line just removes any objects, and then I load the FBasics library so that I can do an evaluation to see if there's any seasonality or other kinds of cycles in the data that need to be taken care of, because it's a time series, and so there's some time series functions in this FBasics package. First I read the data into a variable called failed requests, and then I add column headings. And I take the standard deviation, I take the average, and then I take the create a variable that has the average plus 2 standard deviations. And you can probably guess where I'm going with this. I'm creating a control chart. So I want to create a control chart over time. And presuming there's no autocorrelation going on or seasonality or anything like that, I should be able to get a fairly reasonable estimation as to whether there are any days that had an unusual number of failed requests to successful requests. And in fact, when I run this code, I do identify 3 of those cases, and they're on 3 different days that are shown here on the left. Now we'll do a chart later that will kind of show that. And then after I run that part of the code, the second part of the R code has creates a PDF plot. You don't have to create it as a PDF, but I prefer to. And it just adds some lines. Some of you are familiar with R already, so you know you can add lines. One line is for the average, the other line is for the standard deviation, and also we add a legend. And then the autocorrelation plot is very simple. You simply use a function from that FBasics package called ACF plot, and you take the second column out of failed requests, which has our ratios in it, and the maximum lag is 60, since I know there's 70 some, almost 80 I guess, actual hosts that are in that are grouped together, so I'm lagging at 60 to look for any kind of autocorrelation tendencies. Now let's see if that ran. Yes, and here's our time series, so that ran successfully. Now when you run the R code, you get a control chart, and you see the standard deviation at the top, and you see the mean here in the center. And we see those 3 days, and we can see they are pretty extreme compared to the norm. And then here's an autocorrelation plot, and this shows the tallest bar is at the 0, which means, and there's nothing past this dotted line here, which means there really isn't any significant, statistically significant evidence of any kind of seasonality or autocorrelative tendencies. And we can produce other data sets as well, such as for logistic regression. And here I ran one in Mout, and here's the, ran a number of cases. This one was interesting, I thought. Predictors, the predictors used was host, and I just wanted to see if you use host as a category, do any of them tend to be associated with failed codes? and here's the output, and it's rather lengthy, so looking at it doesn't tell you much, but if you visualize it, just take the output, pop it in a spreadsheet, you get something like this. And on the right hand side, these are cases where the host contributed to failed requests, and it's rather gradual and doesn't go up very high, so we don't have a lot of pattern in this one of any sequence of events leading up to any kind of pattern with failed requests. On the other hand, successful requests in the negative range of the coefficients here have a lot of those, and that's to be expected. It's Amazon data. We didn't load any attack sequences in here, although we had a few isolated attacks. But if there were attacks, it should show something up there if you had a sequence of events leading up to it. In conclusion, Hive provides a very useful framework for analyzing large amounts of server log data. It's a flexible tool that allows drill downs, but it can be helpful to have a collection of queries and methods for analyzing common vectors of attacks as a starting point. Let's hope that the ideas offered here can serve as a catalyst for further discussion and research into this topic.